last video, we proved, or I proved, that this first identity was true. That if you have some angle, alpha minus beta, for the cosine, you can break that up into this first line. And from here, we're going to take what we know about this first line and prove this second line. So this would be the sum and difference identities, right? So this first one is a difference identity because subtraction is often referred to as a difference. And now we're going to do the sum. Okay, and let's see. In the next slide, we'll see that we're going to prove the sum identity for the cosine with the difference identity for the cosine. And there's kind of a neat little trick that we'll use. We always start with our given. And so we know that cosine alpha minus beta is equal to cosine alpha, cosine beta, plus sine alpha, sine beta. And then the little trick that we're going to do is we're going to replace all the b's with its negative counterpart. Okay, so we're with a negative b. And once we do that, we'll have the following. So we plug negative b in for b up above, and we get alpha minus a minus beta is equal to cosine alpha, cosine negative beta, plus sine alpha, sine beta. So right here we have a negative negative, or minus a minus. So if we're subtracting a negative value, that's the same thing as adding a positive value. So we can fix that right away. Now we need to look at these two values here. The negative beta here for the cosine and the negative beta here for the sine. And to do that, we have to kind of remember something that you should have learned during a previous pre-calculus course. And that is to say stuff about the even and odd functions. So an even function is a function that if you plug in a negative value for x, then out will come the same output value for the positive side of that. Now, y equals x squared is an even function, right? Because if you plug in 2, out comes 4. And if you plug in negative 2, also out comes 4. Another way, there's a visual way to see this. You can see that it is symmetric about the line y equals 0. I mean x equals 0. And so we can fold along this line right here, and the right-hand side of the curve will lie right on top of the left-hand side of the curve. And the same is true with the cosine function. So we can, let's see if I can get this going. It looks something like this. You know, you have to use your imagination with my sketches, and it's really slippery on this tablet. So, so you can see that we can go right down the center here and rotate this around and fold it, and this side will lie right onto that. This portion will lie right on top of this portion. This part of it will lie right on top of that part of it. So it's an even function. And so what we know is if you plug in a negative beta, out will come the same value as the cosine beta. Another way to visualize this is on the unit circle. So if we say that this value, this angle right here is beta, then the x-coordinate is the same as the x-coordinate for this angle down here, measured as negative beta. And it's the same reason that the symmetric solution for solving cosine functions is the negative of the preliminary solution. If you watch some of my previous videos, that would make more sense. Okay, so now with this information, we can take all of our cosine negative beta, or our cosine negative beta, and plug in cosine beta for that. Okay? But it's not the same for the sine function. The sine function is an odd function. And odd functions are symmetric about the center or the origin. It's more of a rotational symmetry. So a function that you may recognize as being odd is, oh, that wasn't very good. Let me try that again. Is y equals x cubed. So it goes right through the origin, and you can rotate this top value, or you can rotate this whole curve 180 degrees. And so let me draw a straight line that'll show 180 degrees. And so if you take this point all the way over here 180 degrees, and all the other points by 180 degrees, and it's centered right here at the origin, this bottom part right here that goes towards negative infinity will become the top part that goes towards positive infinity. And the top part that went towards positive infinity now rotates to this point right here at negative infinity. My drawing should be a little bit more symmetric. These points should be, I was imagining them as the point -1, -1, and the point 1, 1. So this is an example of an odd function. And so sine is also an odd function. So if I just draw half of a period on either side, you can see that this point right here is pi over 2, 1. And this point right here at negative pi over 2 is equal to -1. So when the angle is negative, then it is equal to negative the value of its positive counterpart. And this can be seen on the unit circle as well. Let's see. If you take a value of pi over 4, the sine value there is the square root of 2 over 2. But if you take the negative pi over 4, then the sine value for negative pi over 4, it's in the fourth quadrant, so the sine and the y values are all negative. So this would be a negative square root of 2 over 2. And the same can be said about any value. So that means we can take all of our cosine negative b's right here and replace it with a negative sine beta. Let me try that again. We can take all of our sine of negative betas and replace them with negative sine betas. Okay, and that's what I did on the next slide. So here we have this negative beta right here, cosine beta. Cosine negative beta has been replaced with cosine beta. And we have sine of negative beta has been replaced with the negative sine of beta. So now what we have is cosine alpha cosine beta plus sine alpha times a negative sine beta. But if you take a positive value and multiply it by a negative value, you get a negative quantity. And so this would be plus a minus, which can be replaced with just a minus, which is what I've done here. And so there you go. Here is the sum identity for cosine. And our goal has been met. In our first video, we proved this one. We've just proved this one, and now we're going to go on to this one. And we're going to use what we know about the ones we've already proven to prove this one, along with a few other givens that we know about the sine and cosine curves. So we know that the sine curve is a pi over 2 shift from a cosine curve. And we can say cosine is just a shifted sine curve. So we'll start here. We have a positive sine x, and that's going to equal to this shifted cosine function. We're going to substitute in for x, a plus b. So we'll put a plus b in for x here and in for x here. Now, with this, at this point, we need to distribute the negative sign to both a and b. But what will help us here is we're going to group the a with the pi over 2. Now we can use what we know about the difference, so the difference formula for cosine, and expand this side of the equation. Pi over 2 minus a is our alpha, so we'll replace all the alphas with pi over 2 minus a, and then we'll replace b's with for the betas. And I've done that here. Now, at this point, we grouped it in such a way that we could use what we know about the cosine of pi over 2 minus a. That's equal to the sine of a, because the cosine of pi over 2 minus x is equal to the sine of x. So the cosine of pi over 2 minus a is equal to the sine of a. Then we're going to replace the sine of pi over 2a with the cosine of a. I've replaced the cosine of a with the sine of a, and the sine of pi over 2 minus a with the cosine of a, and now we're done. We have the sum identity right here, and now we have done this one, we have done this one, and we have done this one. And finally, we are going to use what we just proved to prove the difference formula for the sine of alpha plus beta, in the same way that we proved the sum identity for cosine alpha plus beta. So we start with the sine of a plus b is equal to sine a cosine b plus cosine a sine b. Okay, and then we do our substitution. We're going to replace all the b's with negative b's. So this is going to be a negative b, this is going to be a negative b, and this is going to be a negative b. And so here's our negative b, and negative b. So we take our negative cosine and we replace it with the cosine. So instead of having a cosine of negative b, we're going to have a cosine of positive b. And instead of having a sine of negative b, we're going to have a negative sine of b. And so that goes into the formula as well. And finally, at this step right here, when we take a positive times a negative, it becomes a negative. And when you add a negative, that's the same thing as subtracting. So we replace that here, and we now have the final sum and difference formula for sines and cosines.